Okay, so we are going to correct all the exercises we had. We have to start by these ones. These are conversion factors. And here, well, we have the first one. It's very easy. We just, for you to remember, we write the unit we have in the opposite side of the fraction, and then the unit we want to convert in the blank part. In this case, the centigrams are down and the kilograms are up. But it can change. I'm not going to comment on all of them because I think you know how to do them. But if you have any doubt, please ask me in the day before the exam or by email. I will answer in emails with a video if necessary. So here we have the typical one from kilometers per hour to meters per second. This one is a bit more complicated one. We saw it, and that's because here, as you can see, we have the milliliters. Okay, we have the milliliters, and we don't know how to transform it to cubic meters. So what we do is we first convert the milliliters to liters because that we know how to do it, and then the liters to cubic decimeters because we know 1 liter is 1 cubic decimeter, and then we transform the cubic decimeters to meters, and that's how we get this. Okay, so yeah, this is a bit more complicated than the other two, but not so complicated. I hope you have it. Another one from hours to seconds. I'm going to go fast because you can stop the video whenever you like and you can copy at your pace. And so I don't want to wait here at the time that you will need to correct it because it's not needed. You just stop the video and do it, okay? But I will continue. So to be a bit fast, here you have another one from kilograms, and here cubic centimeters to cubic meters, and here centimeters and minutes, nothing difficult here. Millimeters to meters and hours to seconds, again, not so difficult. Um, Milligrams to squared millimeters, again, nothing too nothing too special here. Just remember that when we have surface area, every step in the ladder is 2 zeros, so 100. Then we had another conversion factor exercise for you to practice. Again, this one we had an example already, and this one is similar to the one we just saw in the other exercises. 10 days and more exercises to convert units. I hope you have them all right, but please let me know in class if you have any doubts, okay? If you make a typical mistake that you do it always. Yeah, again, here we have from liters to cubic meters, so we are going to use the conversion that 1 liter is 1 cubic decimeter and that 1 cubic meter is 1000 cubic decimeters because it is cubic. So one step, even if from meters to cubic decimeters is only one step in the ladder, is 3 zeros because it's cubic. So that's easy. We just need to convert the hours. And then we had some exercises from the book that were also to convert. So I'm going to go fast with those two. Sorry for I copy the that from the book, from the digital book. That's why it looks so bad. But the answer, I think it looks good. So it's the same process that we did. I hope you really rock it in the exam because you have if you have done all of them, you have practiced a lot. So now order the following values in increasing order. For that, we need to convert them to the same units. So we convert the picoseconds to seconds, and if you look to the ladder, pico is so 1 second is 10 to the 12 picoseconds. So now and same with nano is 10 to the 9, and with micro is 10 to the 6. So if we convert all of them, you see that the smallest one is the one that has the higher number, because all of them are negative. So it means you have more decimal in that. So the first one is smaller than than any of them, and then it will be micro, and then it would be the nanoseconds. So in the end, what we have is this would be the order, okay? Because we have a lot of nanoseconds, so that's why even if 1 nanosecond is smaller than 1 microsecond, 200,000 nanoseconds is a lot of nanoseconds. So it's much more than uh, 2 microseconds, as you can see when we convert it to seconds. Then the same, but now with bigger units. So we convert them to grams, for example, and we have now the exponent is positive. So now the biggest number means actually the biggest number. So the biggest exponent means the biggest quantity. In that case, the one in the middle is the bigger one, and the smallest one is the bottom one. So in the end, if we want to order them in decreasing order, the teragrams is the smallest, the biggest one. Then we have the megagrams, and then the kilograms. Again, it's not 1 kilogram or one. It's because we have several units. Okay, so yeah, so these are the results. One more of converting and then express the result in scientific notation. So for this, we convert it and then we express it in scientific notation. Please remember that the only requirement is that the number before before the comma is between 1 and 9. So in this case, that is met, is 1.5, so perfect. And then you have here several changes. They are all the same. And again, if you want to stop the video to correct at your own pace, do it. But I'm not going to comment on all of them because that would be really boring. Here I'm seeing that you cannot see it very well, but it's cubic centimeters. One more to practice, and again, this one, I mean, is the continuation, but this one, remember, this is micrograms. So yeah, we have all these conversions, and again, I'm not going to comment on them because you can stop the video to correct them. Here we have again the conversion with the liter to be able to put it in cubic meters, and yeah, more of the same here. Again, it's for to practice the conversion. There was a comma there, but it was a mistake, so it's 1 comma 0 is the same as 1. Anyway, number 17. I'm sorry for this. It's from the book, and I don't know why the quality is so bad. So express the quantities with scientific notation, and this is again the same exercise, so easy. You can stop it and watch it. I'm going to go through because I don't have anything to comment on here. So more activities. Those are a bit more complicated, and I saw it in class, but maybe I saw it very quickly, so I'm going to take my time here, and please ask me any doubts in email if you have some, okay? So represent this function and indicate if it is a proportional or a linear function. To represent a function, what we do is we take some values, the values that I want, and for it to be easy, I'm going to take 0, 1, 2, 3, 4, 5. You can take any number you want, but it's easier if you don't take decimal numbers. And then I put it in the formula, and then I obtain what y is. And I obtain those values. That's only using the formula. And then I plot it in a graph, okay? And I see this. If I compare it with the graphs that we have in theory, the direct proportionality, it has to go through 0, 0. If it doesn't go through 0, 0, it's not direct proportional. Okay, similar, but it's not directly proportional. So every time we have a straight line, it can be only these two options, either a directly proportional formula or a linear formula. In this case, because it doesn't start in 0 and it doesn't go through 0, 0, but it's a straight line, it's a linear function, okay? It's a linear function. The thing is that because the slope, the minus 2, is negative, it's going down. It would be the example if it were a direct line, if it were going to pass through 0, 0, that would be the example of less, less, okay? Because here in purple, you have the example of the more something, okay? But if that went through the 0, that would be the example of less something. Well, anyway, no, that's not actually true. But I mean, nothing. That is a linear function. That's the only thing I want to say, because it's a line and it doesn't start in 0. It starts in 5, so it doesn't go through 0. Anyway, so this is the formula as we had in the theory. Okay, I'm not going to ask this in the exam anyway. Okay, but this one I can ask it. So because I'm not going to ask about linear, I'm going to ask about directly proportional, inversely proportional, and this one here, that is the parabola. Okay, this is the quadratic, because we are going to use this a lot in physics. So actually with this, with dropping objects from height. So this is a very important exercise. So the first thing is that we have collected some values, these values, and that we make the graphical representation. So we put the time, because the time is always the independent variable, because it goes and goes away. I mean, and nothing depend, and so the time doesn't depend on the height you throw the object through. Is the other way around. The time it takes, so the time is going to, anyway, so we normally put the time in the x, because normally it's the independent variable. So but here actually I'm saying it, but you could do it any other way, because you could do it any other way. So if you have done it the other way, it also works for me, because we will see it when we need to really work with this. But normally, again, we put the time in the x, because normally is the independent variable. It doesn't depend on anything. So, so we plot the graph, and you see it's not a straight line. It's not an inverse proportionality. What this is the quadratic function. It's a parabola. So here, I mean, if you have plotted the other way around, still you're going to see a curve. So I don't mind. What we have is that we need to calculate the constant of proportionality. This is a typical formula for a parabola. This is the quadratic function, because it has a square in the x. Okay, that's why we call it quadratic, because the square is related to el cuadrado. Okay, so that's why it's called quadratic from Latin. And anyway, so this is the formula, and this you have to know it for the exam. Okay, this is the formula for the quadratic function, and but with our variables, the independent variable is time, the height is the dependent variable, and the k is the constant. So I don't know how you have done it, if you have plotted the other way around the things, because then it wouldn't be the quadratic equation, but it would be a squared equation. So I recommend that however you have plotted, now you use the fact that the time doesn't care about any other thing, and that's the independent variable, and you use it instead of the x. Okay, so that will be it. Now, how do we calculate the k? We could take only one value. Okay, what we are going to do is we're going to solve the k, and we're going to pass the t squared to the other side, and it's going to divide. So it's going to be h divided by t squared, and we have the values here, so we calculate this for every couple of values. Okay, we calculate it for every couple of values. It's very similar, especially in the last ones, because I think they are more precise. When we have less time, it's very difficult to calculate things, and that's why everything is less precise and it's not so similar. So, because the values are experimental, we commit errors, especially I am saying when you hit the chronometer, it's really hard to hit it really quick when the time is so short. So that's why, again, these values are more similar than these values, because those with shorter time are more difficult. Anyway, so which is the good value for k? I'm guessing it's something similar to this, because we have a lot of numbers related to 4.9. So, but anyway, I'm going to take the average of all the values that I have calculated. So if I take the value, sorry for that, that would be the average is 4.82. That's the k. So the formula would be h equals, and instead of k, we put our value, that is the average of all these numbers. What we do, if you don't know how to calculate the average, you sum up all of them and you divide it by the number of numbers we have. So 1, 2, 3, 4, 5, 6. So you add up this and this and this and this and this and this, and then you divide it by 6, and that's how you obtain this 4.82, which is the k here. Okay, the average k, la media. And yeah, so calculate the distance the object will have traveled after 3 seconds. So now that we have the formula, when they tell us that there's 3 seconds, so we just put it in the formula and we calculate it, and that's 43 times 41 meters. So consider the function. Now this is another graph. See, this is the same example of a quadratic function, except that we have here a different constant. So make the graphical representation between 0 and 5. Well, the first thing is to have a table with the values, and to do it we just put the value here of the value we have, and we square it and we multiply it every time, and that's how we have the values. Then we plot them and with a program, because otherwise it's very, very difficult, and we have this. And we can see again, this is this curve that is going up. So it's a quadratic function. Remember, the inverse proportionality is a curve also, but going down. So this one going up is a parabola, and we know it also because it's a squared function, quadratic function. So from the graph, calculate the value of x, considering that y is 131.2. So what you should do, but here is very difficult because the numbers are so big that having that is like really, really hard. You should put a line from the y that is 131.2 and see which number of the x it hits, and it hits the 4. So the value of x that corresponds to that value of y, it's 4. But we could have just checked in the table and guess it from there, because see here, we have that from this value of y, it's 4. Okay, so easier than in this graph that where the numbers are so big that 131 is really, really impossible to see. Next, it says that we calculate the value analytically, considering that x is 4.1. So we are just going to put it in the formula. Instead of x, we put the value, we do the power, and then we multiply by 8 times 2, and that's what we have. Next exercise, 26. That says that a glass contains a liquid that is at a temperature of 60 degrees, and the temperature in the room in which the glass is located is 10 degrees. As time goes by, the liquid in the glass cools according to the following values. So we have here the values, okay? Represent the values in the table. So we represent the values that we have in the table in a graph. And again, I'm going to plot always, please try to plot the time here because it's always the independent variable. And whatever you have over, that's the dependent variable because everything depends on time. Time just goes by. It doesn't depend on anything. It just passes. So that would be the right plot. If you have done it any other way, it's okay. I don't care about the graphs. The only problem will be with the formula. Okay. So we see here that if they tell us which type of relationship do the two variables have. So if we check it with this graph, without a line, we can see it looks like an inverse proportionality. But what about this guy? This guy is ruining all our graph. So we are not going to take it into account because sometimes, again, when we are working, we are making mistakes, and we when we are working, I mean, when we are in the lab, when in the experiments. So this is a mistake, an error in the measurements. So I'm going to just ignore it. And these ones look like a inverse proportionality line. So I'm going to work with that. That is the formula for inverse proportionality. And then I'm going to put the quantities that I'm using. So for x, I'm using the time, okay? And for y, I'm using temperature. And then I don't know the constant, so I put k. But the next step is to calculate the constant and express the mathematical function of the graph. So again, I do a table with my values, okay? And I solve it for the k, passing the time to the other side, and then it's time times temperature. I do the calculation and I get this, and I multiply these two and I get this. So they are similar. They are all around 270 something, but I cannot take one specific value. So I'm going to take the average of all of them. In this case, I have 4 values. So I'm going to add this plus this plus this plus this, and I'm going to divide the result by 4. That's how I obtain this temperature. Okay, this is the temperature I obtain. And then the formula, the one that I have, is the same as I had before, but now I know the constant, so I'm going to put it. Because remember, in the formula, I just need to put the quantities I have without values, and the only value is the one for the constant, okay? I don't put the letter for the constant, I put the value. But the quantities for the general formula, they have to be with letters, because if I put values, that's not the general formula. That is one example. Okay, like for example here, if I put 18 here and 15 here, that is one example. It's not the formula. Then calculate the time needed for the temperature to be at 30 degrees. Because now I have the formula, I just have to put 30 in the temperature, and I just need to solve it for t. So t comes to this side and 30 comes to this side, dividing. That's how I have 9.1 minutes. Of course, minutes, because I was measuring everything in minutes, so that's my unit. If you have put it in seconds, like all the time, all the times in the table that you construct and everything, then it will be seconds. That depends on what you have done. Yeah, let me know if you understand this, because I'm really concerned that you don't understand this kind of exercises. Because again, I'm not going to ask for the linear one, but I can ask for a quadratic function or inverse function, so please understand those. And here there are more activities about expressing numbers in scientific notations, and I think those are easy. So here they are. I'm not going to comment on them. Then again, expressing in international system units. Nothing too complicated here. So there you go. More conversions, so nothing. And the last one is the one that I'm interested in, because it's again something with graphs. So we have studied the relationship between the pressure and the volume in a gas as a constant temperature, and we have obtained the following values. So we have the values here. Represent the values on a graph. So we represent them, and we realize that is going to be an inverse proportional function. So study the relationship between the two variables. It's inversely proportional, and we know it because of the graph, okay, because it looks like an inverse proportionality graph, but also because if we look at values, we're going to see that the more volume, the less pressure, and the other way around. So that is the formula, okay, that is the formula. But if we, in general, I mean that this one here is the formula in general for inverse proportionality. Now we have to put what is our independent variable, what is our x, and what is our y. In this case, we have plotted here volume, so that is the x, and the p is the y, okay? So, because we have it in the table. Normally, so normally the first one we have is always the independent variable. The only exception is that if you have time. There was another example that time was the second quantity, and time is always the independent variable, okay? But if you don't have time, the first one you encounter, so in this case volume, is going to be the independent one, and the other one is going to be the dependent one. So now if we put, so we know that y is the dependent variable, that's p, and the x is the independent variable, that's v. We can put it in a table, and we can find the mathematical function that defines the graph. How? Just finding the k. So we have, that's the formula, and we are going to solve it for k. So we pass the v to the other side, that's p times v, and we do the calculations. Again, it's really close to 60, but we have some deviation because it's an experiment, so there's always errors in the measurements. So again, I'm going to calculate the average of these 6 values by adding them up and divide it by 6. So what I have is this one, that I can round it up to 60 if you like, because it's really close to 60. But if we keep it, that would be our formula. Remember that again, in the function, in the mathematical function, we just put the value of the constant, but we leave the quantities with the letters, okay? Because if you put numbers in the quantities, then it's not a general formula, it's an example, okay? For the general formula, again, I repeat, we put the letters of the quantities and the value for the constant, okay? The value only for the constant. Please do not write P as any of these examples or V as any of these examples. Write the letters, okay? For the general formula, we need the letters, and just this is because this is the constant, it's not a variable. We don't write the values for the variables in the mathematical function, just the numbers for the constants. Then, now we have an example. What volume in cubic centimeters would correspond to a pressure of 2.6 atmospheres? So, now we have an example, and now we are going to use the pressure is 2.6. Now we put the value, but because this is an example, okay, this is a specific example, it's not a general formula. So we put this value and we solve it for V. That means that V goes to this side, multiplying, and then 2.6 goes to this side, dividing, and what we have is this value in liters. Which of course I think I didn't do it, but that would be in cubic centimeters is the same as milliliters, so it would be 23,007 cubic centimeters, okay? And that is it. Those are the exercises. Please let me know if you have any doubts. We have one day before the exam to solve them. If you have them in email, please let me know. I will answer you immediately. And that is all. Please write. Bye bye.